Q over here, right, in this section, and a minus 2Q over here. So if I enclose a foot of Gaussian surface around both of them, how much charges are in there? There's minus Q total, right? And if you think about it a little bit, if I'm to the left or the right of this, it doesn't really make any difference as far as the electric field. I'm looking at a total charge of minus Q in that box. And so what is the electric field? If I covered all this up, I just said, well, inside here is minus Q. What must be coming out of that box on both sides? Electric field lines, right? Or actually going in or going out? Going in, so there must be. And they would have to have some number of them, right, going in. And how many would come in on both sides? Or if I draw it like this, I'm drawing them coming in. Right? In the end, when I integrate, over this area, right, I have to integrate, say, these field lines on the left and the right. I have to see how much charge on the inside. Again, on that Gaussian surface, it has to be minus Q total, right? So, where is that charge going to appear? If I know there's a total of minus Q in here, and I know there's just as many lines coming in on the left and the right, these are the hard part of it. How much charge is over here on this plate, on this surface right here? Well, it has to be the same as over here. How much is that? You're not following. All right, so I know that if I integrate, integral E dot dA over this Gaussian surface right here, I enclose two pieces, right? I enclose a total charge, again, I'll assume it's a unit area. I get a total charge of Q, because I had, or minus Q, because I have minus 2Q from that plate and Q from that plate, and so that will leave me with Q over epsilon naught. Okay. Now, where did that come from? It came from integrating E dot dA over this side, and integrating E dot dA over that side. Those two fields are actually equal on both the left and the right side. So that meant that one part of this, half of this Q over epsilon naught came from this plate, and half came from this plate, from that side of the plate. So how much is over here? How much is on this section? Must be minus Q over 2. So if I were to draw things here, I'd say on this side, there must be minus Q over 2 lined up over here on that surface, because that's what terminates these lines. And over here, there must be minus Q over 2 over on this surface, because that terminates those lines. There's no way around it. Otherwise, when I did this Gaussian integral, I wouldn't get Q when I surrounded that region. Okay? See why this is harder for sure than anticipated. Now wait a second. There's minus Q over 2 here, but there's a total of Q on that plate. So where's the rest of the charge? I got minus Q on, if I look over here, I said I got minus Q over 2 on this face, but there's a total of Q on it. So how much is, there must be some over here, right? How much charge is on this face right here? Take a wild guess. must be 3Q over 2. Otherwise, I'll never get plus Q. So there has to be plus 3Q over 2 here. Okay. How about on this one? I've got minus Q over 2 on this face here, but I need a total of minus 2Q on that plate. So how much charge must be over here? Minus 3Q over 2. It's not got equal charge on two faces, right? They're different. But the sum of the total charge on this face, which is a whole series of minus guys here, right? This face and this face have to give us minus 2Q. And so if you look at the inside, notice that there's 3Q over 2s, and there's Q over 2. It has to be 3 times more intense on that side. Right? So if you were to draw it, and again, I'm telling you, this is harder than I would hope to have given or expected to have given an exam. It would have to look like that. Right? Not trivial. Definitely not a trivial problem to work out. It's actually application of Gauss's law and charge conservation, or making sure you get the total charge. But the key step is this one, recognizing that when you look outside this thing, you get a total charge of Q. Anyway, there's some other things that are a bit subtle about it. recommendation is you think about it, that you work through, make a little sketch here, label with minus q's and 3 q's over 2, see how that could work. The other limit, which you could look at, is if this was plus q and this was minus q, not minus 2q, but plus q and minus q, that'd be just like a capacitor plate. Remember what happens at that limit? You just get a constant field between the two. And so this has an additional field substituted on top of it of a minus q from this plate. So that we look at. So you could have done it by just saying, I know what this, if I just had plus q here, I know what that looks like. That would be, charges flowing out of there. And I superimpose on top of that a solution which is minus 2q, which is twice as many going in. And that will give you exactly the same pattern. Right? So if this is too confusing to think about both plates at once, just do one plate. Draw that. Electric field. Then do the other plate, which is twice as strong going the other way. And then add those two. Some places the lines will oppose each other, they'll cancel, and other places they'll add. And that will give you the same pattern of one strength here, 3 times as strong here, one strength there. So that's probably the easier way to do it. So this is about planes, about charge planes. And I gave some examples of them, double, single, and stuff. And actually there's another one that shows up here. The last one on this part, so that was actually a hard part. The last one is pretty simple. It says pulse the voltage at position x, y, z is V over x squared plus y squared plus z squared. Sorry, V over x squared plus y squared plus z squared, where V is a constant. And what's the electric field? So I gave V is equal to V, which is a constant, for x squared plus y squared plus z squared. All right, so I'm asking for the electric field. How do you find it? I'll tell you what the main mistake is. Yeah. Gradient. Yeah, so the first thing and the biggest mistake people made was this is a vector. This electric fields are vectors, which means I need to have the components. Magnitude and direction would be fine. It's easier just to get the components. So I want an x component, a y component, and a z component. And the biggest mistake was people didn't give me a vector. Again, some version of this is a real exam. So the thing to remember is that it's minus the gradient, or the x component is the rate at which v changes with x. With a minus sign in front, that was the next biggest mistake, that we created the minus sign. And then v changes with y, that's the y component minus the rate at which v changes with z. And the only thing, if people got that far, the only trouble they had was actually just getting the derivatives right. So it's not too bad. Really simple function. All right, so minus sign, and if I take the derivative of this function with respect to x, first thing is I get there's this x in the bottom here, right? So that's to the minus 1 power, right? So I'm going to get another minus sign, minus, and then this thing is going to get on the bottom. It's going to square it up and go to minus 2, if you will. So it's x squared plus y squared plus z squared. So it's actually kind of a nasty function. And then I have to take the derivative of the stuff on the inside. That just gives me 2x. And of course I still have the b on top. And actually this shouldn't be minus 2 down here. That's of course 2 down here. If I left this on top, it would be minus 2. All right, so taking a derivative lowered the power of the thing on the bottom by 1. And then I have to take, this went to 2. I get out that minus sign, and I have to take the derivative of the stuff on the inside. That was just the x component. Of course, you get something very similar for the y, except where I've written x up here, I get y. So this will be minus 2y over x squared plus y squared plus z squared, and squared, and of course you can see these minus signs go away, so that'll just give me, for the z component, 2zb over x squared plus y squared plus z squared, again, squared, and that's the that vector. And you could clean this up if you wanted a little bit, but there's nothing to substitute in. I wasn't looking for something to plug in the calculator. I just wanted to know if you understood how to take gradients and how to go from V's to E's. Yeah?
For the C part, how can we justify that the number